Hello everyone, my name is Victor and so I'm here to present my so I'm going to start with module one, that is AI history, trends and future. So AI is the field devoted to building artifacts capable of displaying in controlled when understood environments and over sustained periods of time. Behaviors that all we consider to be intelligent, or more generally, behaviors that we take to be at the heart of what is have what is to have a mind. So here AI we are considering to develop something like we consider to have in mind, so something like an act intelligent. So AI is demonstrated when a task is performed by a human and though as requiring the ability to learn, reason, and solve problems can be done by them. So here AI is like demonstrated like for example like the task like that can be performed by a human, it can be performed by a machine. So we also have the dimension of AI, which include think like human, like that is to model human cognition, like to model how humans like think. So think rationally, that is formalize the inference of processing. Like here, like we are formalizing, like we are reducing inferences. Like act rationally, that is doing the right thing, like doing the right thing as someone like could be doing the right thing. For example, if they tell you like what is computer science, then you answer the correct answer. So that's like acting rationally, and then act like a human. That is exhibit human behavior, like to act as a human, like as an animal. For example, like how a human can behave, like you can also do the same thing. So this takes us weak versus strong AI. So weak AI aims at building machines that act intelligently without taking a position of whether or not the machines actually are intelligent. So I think this is what we have in the current like weak AI, like it aims at building machines that act intelligent. For them they don't based on the position whether like the machines are actually intelligent. Then you have strong AI. Strong AI is the field devoted to building persons. Like here we are considering like to build like a real person, like someone like for example to get a machine like can act as a real person, like what a human being can do, then the machine can also do it. So it's like we are developing like something like would generally think in a human sense. So this takes us to this takes us to AI technique. AI technique is a method that expresses knowledge and should be represented in such a way that knowledge captures generalization understood by people who provide it and easily modified. So AI technique is like it's like a method that expresses like knowledge and should be presented like such a way that knowledge captures generalization and understood by people who provide it and easily. So to build a system to solve a particular problem, we need to consider like to define the problem precisely, like we define that problem precisely, and then we analyze the problem, like we pass through the problem, like its outcomes, and then isolate and represent task knowledge, and then choose the best problem solving technique. Like here we choose like the best solving, like that technique that can best like can solve that problem in a good way. So this takes us to a different program. The different program is like program that can answer specific questions. It is meant to be solved, like modification in the program leads to change in the structure. For example, this was to a different program before programming the AI. So modification may lead to affecting the program adversely. So when you modify the program, like it can be affected. The whole program can be affected. So programming the AI, like program can answer generic questions. It is designed to solve modification. Like here the program cannot answer a specific question, but it can answer the general problem. For example, if the problem is about algebra, it can answer all the problem in algebra. So we have like modification. The program does not change the structure. So when you modify the program, the structure of the program does not change. Like quick and easy program modification, like it is easy to modify a program. So for example, okay, consider when I consider our virtual reality classroom project, prefix the shift from symbolic artificial intelligence to deep learning. So in the past layer, they used to to develop artificial intelligence like follow follow rules, but here like we are considering deep learning. So earlier artificial intelligence used to rule-based expert systems. Today we use immersive neural education. Like according to Gardner, that intelligence, the project is linked to spatial intelligence, that is navigating 3D environments, and linguistic intelligence, that is learning, and that is learning because like in linguistic intelligence, like we deal with language, something like is learning content. Like unlike strong AI that replaces human, our project demonstrates weak AI augmenting human learning, not replacing. So we are not about like our projects are, it's not based on strong AI, it's based on weak AI. So this takes us to the second module, like introduction to problem solving in AI. Here we come up with heuristic functions. Like a heuristic function is a function that estimates how close a state is to a goal. It takes current state and return estimated distance to a goal. For it, like you just like I think you just estimate. The heuristic function, they speed up exhaustive brain searches and provide educated guesses about promising paths. So when creating heuristics, that is problem relaxation, we follow a standard approach. For example, like when we are creating a heuristic function, like we follow a standard approach. That is starting with optimal problem, like we start with the small problem, and then we remove all relaxed problem optimal, like we relax the problem, and then we solve the relaxed problem optimally. Then use this solution as a heuristic for the original problem. So the heuristics from the relaxed problem are either admissible or inadmissible heuristics. So admissible heuristics do not overestimate the current cost to reach the goal. For them, they do not overestimate the current cost to reach the goal. They do not return a value better than the actual cost. For them, they do not return a value for the actual cost. I think when we mean by cost, I think like what are you going to like those things we're going to incur during like solving the problem, and then the guarantees to optimal solutions. While inadmissible heuristics may overestimate cost. For them, they may overestimate the cost being faster, but may miss optimal solutions. So the trade-offs in heuristics, like the quite a vast speed, like trade-offs mean like what you have to sacrifice in order to get something. So the trade-offs in heuristics are like quite a vast speed. More accurate heuristics take more computation time. Like here, you have to decide between quality and speed. So you have to to measure whether I go with the quality or speed. Then like composite heuristics, like here this combines multiple heuristics for beta accuracy. So you can either combine all the heuristics for the beta accuracy. Then this takes us to the search strategies under this include like the best fast search. So the search strategies under heuristics like include the best fast search, like combines advantages of the first and very fast. So for the best search, like you go with the with the first one, you see which is the best, and then you use the 06 to guide the search direction. Like and you also have hill climbing. Hill climbing is the same as like as usual as you climb a hill. For example, you move from one step to another, so you see the best step. You can't climb like when you're going down. So you have to see the highest position, and then you climb that one. So here they say always moves to the better neighboring state, but this has like drawbacks such as local maxima, like gets stuck at peaks that aren't global optimal, then plateaus like high flat areas, like with no improvement direction. For example, when you're on a flat land, like with no improvement, you don't know where to go. But when you're on the hill, like you know where to go. Like I'm climbing a hill, I have to reach a peak. So you follow, you go with the the best next position. Then he also has incompetent, incompleteness. Like that is may never find a solution due to local maxima. Like you will not find a solution due to local maxima. So when I take this back as to the take this back to our project, like when the VR classroom is framed as a problem space, like our initial state should be student outside the class. So here we consider like the students outside the class. So our goal is like student mastering the concepts within the class, like the students like within that actual class. Then operators interacting with others and answering quizzes. So here like we are our operators like interacting with others like those information like either they may be text or the video form. So then data mining like student answers classified into correct or incorrect. So like here students are classified into correct or correct. So according to Gardner's intelligence, here is it is expressed as logical mathematical intelligence, like that is structuring problems into states. So here like we are structuring a problem into states, and then according to philosophy, the frame problem that applies that is which parts like of the VR environment are relevant to learning. So here like we don't know which environments are like we should consider, like we take as our inputs. So this takes us to our third model, like problem solving by search. Like here we have uninformed versus informed search strategy. Like uninformed strategy, like also known as blind search, like using information about the likely direction of the goals. For them, they use information. They include depth first, depth limited, uniform cost, depth first, iterative deepening, and then by direction. And then here takes us to like informed search strategy. For strategy, also known as heuristics, as I explained like the current in the previous slide. Like for them, like they use information, they use information about the domain to head in the general direction of the goal node. So they include informed search methods like hill climbing, best first, grid search, beam search, A and A star. So when we look at this as in the course of our project, like the VRR, the virtual reality uses such strategies for navigation, such as like the best first search is like that is progressing step by step through lessons, and heuristic A that's jumping to the most relevant lesson based on the prior mistakes. So here like we are using heuristic, and then like the best first search, like that is progressing step by step through. I think this is the very first start. Like we are going to pass through all the lessons, so like to find out the best lesson. And then heuristics, like we jump the most relevant lesson based on prior mistakes. Data mining, like clustering. Here, clustering lessons by topic reduces such space. So here, when we group the lessons into topics, like that's like we shall reduce the search space. And then according to Gardner's intelligence, the project is linked to spatial intelligence, that is navigation, both physical 3D space and abstract search. So here we look at the spatial intelligence, and we look at like the intelligence based on the space. So we look at the space and then we generate like the physical layout. So the VR's knowledge path is a simulation of both of possible learning, just like a simulation algorithm. So here like we are just simulating, like but we are not like really thinking. So this takes us to the our next module, knowledge representation and reasoning. So knowledge is representation in a hierarchy, that is data. So here when we talk about knowledge is represented in a hierarchy. For example, in Uganda we have a president, prime minister, the vice president, and any speaker. So and also here in the data in knowledge we have like hierarchies. So we have data, primitive variables, variable facts of any representation. So data doesn't have many meanings. So data are raw facts. For example, 1, 2, 3, A, B, C, D. But information processed or interpreted data. So information like what is your name, and then like 1,000 shillings. Like that is information, because like it gives meaning to someone. Like when you talk about 1,000 shillings, like someone knows, like that gets a meaning. Like that is money. But when you talk about 1,000 or one, no one doesn't like. One doesn't understand like what are you meaning. But also knowledge like relation among sets of data information that is very often used for further information deduction. So here knowledge that is like processed information. So How knowledge, representation, and reasoning works. So here we'll look about the steps like how knowledge is represented. So intelligence requires knowledge. So like intelligence requires knowledge. So someone to be intelligent, someone has to like someone requires knowledge. For example, to be intelligent somehow you have to acquire knowledge. For example, to be like intelligent in example in the health center, so you have to first acquire that knowledge about like the health facility. So here we also have computational models of intelligence require models of knowledge. So the computational models of intelligence require models of knowledge. So how knowledge can be represented? Knowledge can be represented in symbolic methods, uses symbols and rules to represent knowledge, and logic-based reasoning, and they include languages like includes imperative languages, declarative languages, hybrid languages, and rules, frames, and semantic networks. So you also have knowledge can also be represented in non-symbolic methods. They include neural network based, they are neural network based approaches, and they include neural networks and genetic algorithms. So when I look at this as in the context of our project, so the ovaries encode classroom rules in the if-then form. For example, I told you that ovaries like they are information that come on the screen of the feed the virtual reality classroom. So here, if a student fails, then show revision ovary. For example, like when you are given in the test, like in the virtual reality form, like and then you fail that form, so the model will give you we show you the revision overlay so that you can review and then you try again the quiz. So according to data mining, like association rules modeled minded from prior student data. So here we associate rules minded from prior students. So like we look at the prior students data, the previous, and then we form association rules. According to Gardner's intelligence, here it is expressed as linguistic intelligence in encoding knowledge as text-based overlay. So I said linguistic intelligence like about like natural language processing. So like you are encoding knowledge as text-based overlay. For example, it reads and then like it understands and how it learns. So this raises the question: can all classroom knowledge be symbolically represented, or is some understanding non-formalizable? So that's the argument we look about. So this takes us to the next module, inference in first order logic. So here exists resolution principle, which is important rule of inference applicable to clauses used to demonstrate unsatisfiability and foundation for automated theorem proving. So here we look at the resolution process, that is convert formulas to clause form. Like here we convert formulas to a sentence form, apply resolution rule to derive new clauses, continue until contradiction found on new clauses. So see how we continue like we are in the loop, like we continue until we found all no new clauses, like we found any contradiction on new clauses. So resolution trace a sequence of annotated clauses separated in two levels. The first level contains the clauses in the initial database. Each subsequent level contains all clauses with at least one parent at the previous level, and then annotation specify the clauses from which they are derived. So here also have soundness. Sound is resolution is sound in that any clause that can be derived from the database using resolution logically implied by the database. So resolution never derives first conclusion from two premises. So here like we are soundness, like we follow. For example, if they say like for example if we give you like a premise, a premise, so you can always arrive at the correct conclusion. For example, if I say that it always like it's hot outside, and then I say it is shining. So and then I give you I give you another premise. For example, if I give you a premise like it's hot outside, and then you give it sign. I say like the temperature is high, so I give you it shining. So you can either live to the correct conclusion. So, and also you have completeness. If something is logically implied, resolution will eventually drive it. So always resolution will be complete. So it will not terminate in the way. So may require paramoduration for equality handling. So when I look at this as in the context of our project, so the system uses inference to provide adaptive feedback. For example, if student shows concept A and concept B, then unlock a device overlay. So here, like, we follow like those rules, inferences, like to provide the adaptive feedback. For example, here we follow like if student knows concept A and concept B. So if you know about the concept A and concept B, then show a device overlay. So when we look at this data mining, like classification results act as facts from which new insights are from. In fact, so here like classification results, like here we can we can use it like to get new ideas. So here logical mathematical intelligence, diving into like here we look at this as a type of intelligence, like logical mathematical intelligence, like in driving new truths. Like here we defining parts, like we are understanding patterns. So this is like Chinese room for problem, that is the VR understand the virtual reality system understands student progress, or it's simply applying inference rules. So doesn't know like you are understanding, or for it just like applying inferences and rules. So this brings us out to our next module, reasoning and understanding. So here we are going to look at probability field and utility field. Probability field, which provides the basis for our treatment of systems that reason and understand. For probability here, we are like measuring something. For example, probability we say like condition and condition. For example, if I say the probability of winning a game, probability of me winning a game is like 0.5. Here, like I'm like I'm like give you like I'm like foreseeing. So here I also have utility field, which provides ways and means of weighing up the desirability of goals and the likelihood of achieving them. So here like we are okay. Utility field provides ways and means of weighing up the desirability of goals and the likelihood of achieving. So here like it provides you the ways and the means of weighing. For example, here like you weigh. For example, if I'm to win a game, what should I be doing? What should I have? What should be I having? So that's the utility field. So they combined when you combine probability and utility, so constitute decision field. So here like take decisions which are uncertain within uncertain domain. So here like you take decisions like within a given domain. So why uncertainty arises? So uncertainty arises due to laziness, like too much work to determine exact truth. So here like when you are lazy, so we have theoretical ignorance, no complete theory available. Then you have practical ignorance, even with theory can't determine exact values. So this takes us to Bayesian networks, like represent knowledge in certain domains, model conditional dependencies, enable efficient inferences. So when we look at this in our project context, here students may provide incomplete input such as unclear speech and any other information. So here the system applies Bayesian reasoning, that the probability student master the concept is 0.5. So is a uncertain overlay is completed. So here, as I said, like probability, like we are based on certain condition and then we make a prediction. So according to data mining, Bayesian classifies predict student understanding from incomplete data. So here, like the Bayesians, like they they just predict, as I said, in probabilities about predicting. So they just measure student understanding from incomplete data. So according to Gardner's intelligence, here naturalistic intelligence is demonstrated that it's coping with noisy real-world signals. So noisy real-world signals are like unneeded data. So for example, if like a model like does what it is not intended to do, so I think that's like noisy real-world signals. So according to philosophy, can probabilistic models ever capture the true uncertainty of human learning. So that takes us out to our next model, that is planning. So planning is the reasoning about future events to establish a series of action to accomplish a given way. So like here, like we are planning, like planning is like in a layman's language, like you introduce, like for example, you plan for the difference. So for example, I'm going to go this, I'm going to do this, I'm going to do this. So here, like planning is like reasoning about future events to establish a series of action to accomplish a goal. So the purpose of planning is to find a sequence of actions that gets from the initial state to the goal state. So here, like we are finding a sequence of action that takes us from the initial state to the goal state. The initial state is like the starting point, and then the goal state is the final point. So a common approach to planning is representing a current state and determining the series of necessary actions to reach the goal state. For example, here, like here they're saying like the common approach to planning here, like they represent the current state. So you represent where you are. So you represent like the data you have, and then you determine the series of necessary actions to reach the goal state. So you determine the ways of reaching that goal state. For example, if I say that I'm going to Kampala, then you are to Wise, so you have to start from Wise. I say when I move to Wise, I'm going to take either one day or Sapo to reach Kampala. So plans are created by searching through a space of possible actions until the sequence necessary to accomplish the task is discovered. So here, like planning, like you search from the space. For example, as I said, you are Chihuahua, and then you want to go to Kampala. Either you can take Sao Paulo or what again. So until you reach the until the given task is accomplished. So planning and problem solving are different because of the difference in the representation of goals, states, and actions, and the difference in the representation and construction of action sequence. So some people take planning as and problem solving but as the same, but they are different in terms of goals, states, and actions. Planning systems here we also have planning systems. We have the situation calculus, the direct or first order logic for changing worlds. We have the STUPS, is an relative representation to the pure situation calculus for planning. Original STUPS used to use the goal stack planning control in its search. So the original STUPS here used the goal stack. So and also you have goal stack planning. This breaks up a set of a set of goal predicates into individual sub goals and attempts to solve them individually, one after the other, but but it's not complete. That is, it can terminate without finding a plan. So this one like has a drawback, like may not complete, like it can like terminate without finding a plan. So this takes us to okay, when we take us that in our project concept. So within the virtual reality quest, like within the virtual reality quest session plans such as introduction, demonstration, activity, and even feedback. So they may follow a given plans, like when I'm going to start with the introduction, demonstration, activity, and then even feedback. So it can plan that if a student fails this quiz, then you introduce the activity before trying. So data mine there is a frequent pattern mining that is system learns the most effective lesson sequences. So according to Gardner's intelligence, bodily kinetic intelligence, that is sequencing physical action. So this is the type of it's like body kinetic. So here like we consider like the human movements, like how they appear. So according to philosophy, the frame problem, how does the planner know which conditions are necessary for the next station? So this takes us to our next module. So this takes us to our next module, that is planning and decision making. So real-world domains are complex and do not satisfy assumptions of STUPS or partial order planning methods. So here, like the real-world domains are complex, like they are hard, they are difficult, and they do not satisfy assumptions of STUPS. So the hierarchical decomposition of all hierarchical task network planning uses abstract operators to incrementally decompose the planning system. So here, like this hierarchy task network is like a form of planning. So primitive operators present actions that are executable and can appear in the final plan. So the benefits of a equal task network like manages complexity, zero abstraction, uses proven solution patterns, scales to larger problems. So the operators with condition effect that have defined effects depending on what the world is like. They are executed. So a decision here like this is like the given effect said a disjunctive effect is used to model random effects that are determined by the precondition of the operator. So when we look at this in the context of our project, so the system makes optimal choices under constraints such as if time is short, then show summary overlay. If time is sufficient, then full lesson. It can also balance engagement time and knowledge gain as utility functions. According in data mining, predictive models guide which path maximizes learning outcome. This shows interpersonal intelligence through self-paced learning and in interpersonal intelligence through collaborative material research. So those are the types of intelligence here we incur. So according to philosophy, AI's decision real rational choices or estimated rationally. So this takes us to our last model, that is machine learning. So machine learning addresses the fundamental of building computer programs that learn automatically from experience. So here we address the fundamental of building computer programs that learn automatically from experience. So here we are demonstrating how computers learn from experience. So machine learning is the most rapidly expanding technical field in the intersection of statistics and computer science and lies at the core of artificial intelligence. So the machine learning is the subset of artificial intelligence. So it lies at the core of artificial intelligence. So types of machine learning, if you have supervised learning, so I think that's learning from body data. For example, if you give a computer a cat and a dog, and then you provide labels that this is the cat and then this is the dog, and that's supervised learning. So it includes classification, this predict discrete categories, and then integration predict continuous value. For example, those are the rain figures. And then you have unsupervised learning, find patterns and unlabeled data, clustering, unlabeled data. Like this include clustering, like group similar instances and association, finding relationship between variables. So unsupervised learning, like you give a computer a cat, a dog, and then you specify and you ask it which is a dog, and then it gives you that's learning. So then you reinforcement learning, learn through interaction with the environment and receive rewards and penalties. So here you based on rewards and penalties. If a computer fails, and then you give it a reward, and then if it passes, then if it fails, you give it a penalty, and then if it passes, you give it a reward. So it's like in our classes, if you fail a test, they give you this amount of, if you pass, then they give you a different marks. So when we look at this as in the context of our project, so here we use DNRF, which is supervised learning, trains on classroom images as a data set to reconstruct the event. So here we provide the model with given data sets, for example, the images of the class, videos, and then it reconstruct the environment. So data mining here, classification that is predict learning outcomes and clustering to group students with similar struggles. Here uses classification that predict learning outcomes and then clustering to group students with similar. So here group students with the same struggles. Though so here the type we incur the logical mathematical intelligence through pattern recognition and naturalistic intelligence through analyzing the diverse signals. So according to philosophy, the debate on superhuman AI, can a machine learning driven virtual reality environment teach more effectively than a human teacher? So here we are arguing about can it replace a human teacher? So thank you for listening.